today we'll have a webinar on the American monsoon. And we invited two speakers, Professor Pedro Leite da Silva Dias and Professor Salvatore Pascale, who will talk about issues concerning the South American monsoon and the North American monsoon. After the presentations, we'll have a session of questions and answers. So please, during the presentations or soon after them, leave your questions in the box of Q&A. Please not in the box of chat, but in Q&A box. Just to introduce the theme. So I will first introduce this theme of American monsoons. There are two components in the systems of the American monsoons, the South American monsoon and the North American monsoon. Just to give you an idea of the intensity of these two systems, you have here in this figure the mean annual cycle of precipitation over some major monsoon systems. And here you have the annual cycle for the core monsoon region in India, in North America, Sahel, in South America. This figure shows you that the intensity of the monsoon system in South America particularly is very strong. There is a very great contrast between precipitation in winter and precipitation in summer. This South American monsoon affects most of South America, as you can see here in this, within this red line, where we have the monsoon domain over South America. So it covers very extensive and very populous regions over in South America. And in this core monsoon region here in Central South America, more than 90% of the annual rainfall occurs during the monsoon season, from October to April. Here we have a figure of the circulation during summer at low levels. In austral summer, we have here a thermal low pressure system over the Chaco region, and then the tropical northeasterly trade winds are enhanced, entering the continent. In this cross-equatorial flow penetrates South America, becomes northwesterly at the Andes foothills, and is channeled southward and turns then clockwise around the Chaco Low. The low-level wind and moisture convergence associated with interaction between this continental low here and the South Atlantic high, and these northwesterly winds result in very enhanced precipitation in this region. So in summer, actually, we don't have a complete reversal of the wind, but the zonal component here in this region, in the core monsoon region, reverses its direction. In winter, it is westerly, easterly from here, and in summer it is westerly. And this westerly component then takes moisture into the central region of South America. What I wanted to emphasize is also the topography here in the continent. we have here the Andes Mountains, which are well known, but here in Central East South America, we also have big mountains, and they have a very important role in anchoring the South Atlantic convergence zone in this region. Concerning the North American monsoon, its core region is here over Northwest Mexico and extends towards the southwest of USA. This is responsible for about 70% of the total annual precipitation in the Mexican portion and almost 40% here in the USA portion. Well, as Dr. Pascale will talk about this, the beginning and the decay of the monsoon season, I will not go into much detail here. Well, let's present the regional working group on American monsoon, which is one of these regional working groups working with this CLIVAR GEWEX-Monsoons panel. We have participants from North America and from South America and even from Europe, as Dr. Pascale and Robin Chadwick. And there is a very good distribution between early career scientists and more senior scientists in this team. This working group on the American monsoon aims mainly to, first, reduce the community's vulnerability to natural variations in the strengths of these two monsoons, the North America and the South America one, and to monsoon climate change, facilitate interaction among researchers, operational predictors, and stakeholders, coordinate scientific community efforts to understand the American monsoon systems and their predictability, and contribute to improve the reliability of forecasts, and provide authoritative information on process understanding, models fidelity in representing the regional monsoons components, and forecast skill assessment. And to reach these objectives, the members of this working group participate and present in climate outlook forums and in workshops on special events such as El Niño and La Niña, which bring together climate researchers, operational forecasters, civil defense, and stakeholders. The members also present or convene sessions on the American monsoon at international conferences and workshops, encouraging researchers in this field, research in this field, particularly among early career scientists, and also provide reviews and original papers on all aspects of the American monsoon. And finally, promote workshops and advanced schools that bring together senior and early career researchers, students, stakeholders. So the first advanced school and workshop on American monsoons took place in Brazil in August 2019. And the second one will be held in Mexico. Here we have a picture of this first workshop and advanced school on American monsoon which happened in 2019. We had even the participation of Dr. Chai, who was the co-chair of CLIVAR at that time. He's seated here. Well, I think now we'll move to the first presentation, which is titled The Challenges for the South America Monsoon Predictability by Professor Pedro Leite da Silva Dias. I will just first introduce him. Let me get the, just a minute to get his CV. Excuse me this. Okay. I have then the pleasure to introduce Dr. Pedro Leite da Silva Dias, who has contributed significantly to the area of atmospheric sciences during a long career as professor and researcher. In addition to having been director of important research and operational institutions, he is a Bachelor of Science in Applied Mathematics at the University of São Paulo, and is a PhD in Atmospheric Science from the Colorado State University. He is professor at the University of São Paulo since 1975. Was former visiting researcher at NCAR, NCEP, and IRD. Was senior researcher at IMPO here in Brazil, head of the Center of Weather Forecasting and Climate Research, director of the National Laboratory for Scientific Computing, director of the Institute of Astronomy, Geophysics, and Atmospheric Science at the University of São Paulo. Is presently member of the Brazilian Academy of Sciences, was president of the Brazilian Meteorological Society, advisor of more than 70 graduate students. His research interests cover complex modeling of the atmosphere, parallelization of atmospheric models, climate variability, weather forecasting, air pollution modeling, role of tropical heat sources, uncertainty estimates in weather and climate predictions, climate change issues, interactions with users of meteorological forecasts. So please, Dr. Silva Dias, the floor is yours.
Thank you, Alice. Let me share my screen. Here it is. Okay, I hope you can see it.
Perfect.
Can you see it? Yeah.
Yes, that's great.
Okay. Let me go over this theme. And for a start, just to start, well, here is a description of the general description of the South American monsoon system, but I can go pretty quickly with that because it has been already described by Alicia. I'd just like to point out that we're very much concerned not only with the organizational precipitation in the core of the monsoon region over South America, but also the South Atlantic convergence zone, which is an extension to the southeast, and the intertropical convergence zone as well. These are important. I'd like to talk about predictability from the user's point of view and from a researcher's point of view. As a user, I actually identify myself as a user because besides being a professor, my wife and I, we run a coffee farm for over 30 years now. And of course, as a farmer, I'm always asking my partner, Pedro Dias, the professor, what's going to happen, right? Not just in terms of when it's going to begin the miss of the monsoon, and the breaks in the monsoon. All these things play a substantial role in our activities here. But now back to the users' wish list. And I talked to a lot of farmers. I talked to people in the renewable energy business as well, because several of our former students are now working in private consulting companies. So I have a pretty good idea of what kind of research they need and what they are supposed to offer to the users. One of the things in farming is how in the central part of South America is how can we feed 2 or 3 crops during the year under natural climate variability, or how to optimize productivity in permanent crops, livestock, using climate information. You see, there is very specific needs concerning the dates for sowing, identify what kind of crop variety you're going to use depending on the what you expect for the beginning of the monsoon, or the combination of different crops during the annual cycle. So it's crucial to have information of the overall behavior of the wet season. And in the last 5-6 years or so, there is an incredible increase in the demand for the subseasonal to seasonal scale prediction. And of course, the weather prediction for planning regular operations, spraying, fertilizing, and so on. And also, something that caught my attention more recently is an increasing demand for nowcasting. So, in fact, not the official service, in other words, the weather service, is not able really to provide all this kind of information. That's what made it possible for these private companies to spread all over Brazil. Another point is sustainable agriculture, environmental certification. Carbon farming is also something important. And of course, what's going to happen with climate change. Concerning renewable energy, there's a lot of interest from the point of view of energy pricing, few weeks, few months. The S2S time scale is very critical. The seasonal prediction is also very important. And as I mentioned before, national services in general, they do not provide the regional information, not responding to specific user demands. There's the operational use, the dispatch of how much energy each company is going to produce, the maintenance, they're very much concerned with weather, severe weather in particular, and this question about dam safety and urban impacts. Another point that has called my attention here is the multiple collocated renewable energy sources. Several companies, actually, they run hydro, wind, and solar. Some that I know run solar and biomass. Well, in other words, they have a combination of these different sources. Can you imagine, from the point of view of the meteorological guidance, how difficult it is to provide information for this kind of user, because they actually want to optimize the use of each renewable source. And of course, there's a demand for environmental certification. Dealing with extremes is the main question here, and future climate, so the sustainability of the energy source. And of course, planning for future installation, which is a traditional system. Why this became so important in the last 10, 20 years? This figure tells you why. We have here the changes in the annual precipitation from the decade from 2011 to 2020 and the 1980-89. And if you look over the core of the monsoon area in South America, there is a significant decrease in the precipitation in the last 10 years. And mostly from 1921, 22, 23, the precipitation has also been below normal. So this is something that is very, very important. Alice Grimm, for instance, she wrote a paper some years ago concerning the decade of variability of precipitation in different parts of South America. And most of them show ups and downs, extracted this particular spot here. And you see there's a substantial change in the precipitation in the decadal time scale. And there's connection with sea surface temperature anomalies in the Pacific and the Atlantic Ocean. Just to make it short, there are some conclusions about the mechanisms that are altering the behavior of the rainy season in South America. Most of the papers show strong connection with Atlantic variability, particularly with the AMO, the Atlantic Multi-Decadal Oscillation Index. It also influences the equatorial mode, the Atlantic dipole, mainly in the northeast region and the northern part of South America. AMO has been in a positive phase for approximately 20 to 25 years. It may take another 4 to 8 years to change phase. There's connection with the Pacific, and so of course, but there's a connectivity with PDO. And with PDO negative, you tend to have below normal precipitation in the monsoon area. So we have more recently a combination of positive AMO with negative PDO, which reinforces the negative signal in the quality of the rainy season in central Brazil. This is something that is worrying because it may, this is something that doesn't change suddenly to a completely different behavior. Something else that the users, both in agribusiness and renewable energy, are very much concerned is the length of the rainy season. There's this paper by Silva and Carvalho, 2007, and they define actually it's principal component analysis of circulation and temperature, moisture, and precipitation. And here the original paper goes up to 2007. But one of my students actually updated this figure, and what called my attention is the fact that the onset of the monsoon season has been delayed significantly from 2010, 2008 onwards. And that the miss is also coming earlier, 10 days earlier. So as an impact, when you combine the two features, you see a general decrease in the length of the rainy season, which is very concerning for most users. Well, there are other things like the ENSO. ENSO also plays a significant role. You have here the maps, and you see that it's mostly in the northern part, the southern part of Brazil, but there is some signal also in the central part. The tropical Atlantic dipole, this feature here on the right, also has a significant impact, not only over northeast Brazil, but also extending in some important areas from an agricultural point of view here in the central east part of Brazil. Intraseasonal variability has a lot to do with the breaks in the rainy season. So active phases of the monsoon, you have the westerly regime, break phases, you have the easterly regime. And most of the studies show that there's a strong connectivity to the Rossby wave strain emanating from the South Pacific. One of my students recently is studying the phase transition of the intraseasonal variability using self-organizing maps. And the general trajectory, it goes P1, P2, P3, and so on, and back to P1. But it turns out that when you look at the probability of transition from one phase to another, you see arrows that don't go in the regular direction. And sometimes the cycle simply stops somewhere and returns to another phase. So there's a lot of concern about that. And apparently what is happening is the fact that the intraseasonal variability in South America is very complex in the sense that it depends on the MGO, the classical Kelvin wave propagation along the equator, but it depends on the Rossby wave trains. And when you look more carefully at the Rossby wave trains, there is one that is well to the south, as described in this little picture here, But there's also another one about 20 south or so on that travels pretty much east that have a different time scale compared to the regular NGO type, the equatorial type, or the Rossby wave train that goes further to the south. And that's probably what explains the fact that sometimes you don't follow the, the nice circle of categories. And from the point of view of predictability, this is crucial because the S2S people, those guys that are working with the prediction, the S2S category, they rely on numerical models, but they also rely on artificial intelligence, machine learning techniques in order to understand what's going on. There is also, from the point of view of the seasonal to sub-seasonal forecasting, there's this interesting paper. There was climate dynamics, an evaluation of how the models behave concerning the prediction of the week 1, 2, 3, 4. And you can see there is a signal. It's not that strong, but there's something, particularly over the South Atlantic Convergence Zone region. And as far as I know now, talking to my colleagues at consulting companies, they actually have been using a combination of S2S products or extended forecast operation from ECMWF, for instance, plus machine learning techniques in order to get a significant improvement up over the traditional numerical products. So this became really a big business, and everybody's concerned because of the importance of the prediction of this week 3, week 4, even longer periods. And of course, climate change is another important issue. People are very much concerned about is it sustainable to maintain the 2 or 3 crops per year? What's going to happen? Are going to have to move around different areas? What's the expectations in terms of climate change? And it's not just rainfall. It's very much related also to temperature because of the water stress on the plants and so on. And from the point of view of predictability, if you look at products from IPCC, different versions of the IPCC 3, 4, 5, 6, you still have a significant variability in the predictions concerning the central part of Brazil. Keep attention on a point in the center of this picture, and you'll see that there is significant variability. So in general, you tend to have a little less precipitation in the Northeast and even in the Amazon regions in some models, but things vary a lot. And of course, users don't like that very much because you can't really tell with absolute certitude that the impact in a particular area is going to be positive or negative in terms of precipitation. Models, as you can see here, for instance, do have a significant problem in the location of the ITCZ. Here on the left with the red arrows, you have the ITCZ and the South Atlantic Convergence Zone. So different models. You have models with a double ITCZ. Several models have a double ITCZ. Some models have the ITCZ well to the south of the observed position. This is something that I've been putting a significant amount of effort in trying to understand, and the relationship of this positioning of the ITCZ to how well does the model reproduces the AMOC, the Atlantic Meridian Overturning Circulation. It seems that it's very clear that there is a very tight link between having a bad description of the AMOC and having an ITCZ in the wrong place. Another point is the ability of the models to describe the actual behavior of convective systems. You can see on the left here that systems are displacing westward, very organized in the form of lines and so on. With convective parameterizations, you have this off and on system. But when you run high-resolution, solve-resolving models, you seem to have a behavior of convection which is closer to reality. So to summarize, research challenges to improve predictability, intensity, and period. In other words, the breaks and the length of the rainy season and the breaks is very important, seem to be related to problems in the ITCZ location and intensity, AMOC, as I mentioned before. Climate change poses a significant problem there because AMOC versus interhemispheric asymmetric impact of global warming. Each of these effects have a different impact on the position of the ITCZ. Reducing the AMOC tends to bring the ITCZ to the south, but the greenhouse gases warming effect is stronger in the northern hemisphere, and that tends to bring the ITCZ northward. So we have two contrasting effects, and that's one of the reasons why I think predictability of what's going to happen to the ITCZ is not that simple. South Atlantic convergence zone, same thing. We have the Pacific and the Atlantic connections. Hard to really detect with the precision the position of the wave train propagating from the Pacific to South America, and it has a significant control on the interseasonal oscillation, for instance. We have issues concerning the numerical problems in models near steep orographies, such as the Andes. Diurnal variability continues to be a major challenge. S2S predictability, the local control due to soil moisture and geo role. And we have seen an increasing role of AI in improving predictability. And I think that's about what I had to present you today. Thank you.
Thank you, Pedro. Now, just reminding the viewers that they can post their questions in the Q&A box, and they will be answered at the end of the two talks. So now we will introduce then Dr. Salvatore Pascale, who will give his talk. No. Dr. Salvatore Pascale, he is an assistant professor at the Department of Physics and Astrophysics at the University of Bologna in Italy since 2021. His research activity focuses on understanding the impact of climate change and variability on weather and climate extreme events, with a particular emphasis on climate dynamics, Mediterranean climates, and monsoons. He holds a Master of Science in Physics from the University of Naples and a PhD in Meteorology from the University of Reading. Before joining the University of Bologna, he was research fellow at the Hamburg University, Germany, the California Institute of Technology, was an associate research scholar at Princeton University and NOAA Geophysical Fluid Dynamics Laboratory, and research scientist at Stanford University. So now I invite Dr. Salvatore Pascale to give his talk. The floor is yours.
Yeah, thank you, Alice, and thanks a lot to all the organizers of this very nice webinar. I'm gonna share the screen, and okay. Okay. Can you see?
That's great, Salvatore.
Okay.
Yes.
All right. So today's talk will try to give an overview on some of the most outstanding scientific issues about the North American monsoon. In particular, I will first say what it is the North American monsoon for those who are listening who are not experts in the field. And then we will discuss what's the response of the North American monsoon under global warming, and what are the challenges that limit our ability to project and to have a trustable projection for the future. So as it was said by Alice in the introduction, so the regional monsoons are a regional manifestation, a regional declination of a more wider global system, which we call the global monsoon, and which is associated with the seasonal shifts of the tropical rain bands over land. So you see going from July to January, and you focus over lands, you see that the tropical rainfall bands shifts a lot from one hemisphere to the other. And so if you look at Americas, you clearly see the South American monsoon and the North American monsoon, which extends roughly over Central America into Mexico and up to the southwestern US. What you can see from this global picture is clearly that over all the monsoons you have, so the West African monsoon, the Asian monsoon, South American monsoon, and so on, the North American monsoon, which you see here, is the smallest in terms of spatial extent, and actually also in terms of intensity. This was shown by Alice in one of her first slides, okay? So it mostly extends over quite a narrow strip of land, which is Central America and Mexico. So it's the smallest, and this, as we'll see, has been one of the main problems for models in simulating that. So often there is not a general agreement about what we define as the North American monsoon. So traditionally, the so-called core region of the monsoon is the one which extends over northwestern Mexico into the southwestern US. So if you look at the seasonal cycle of rainfall here, which is this one, you see a clearly unimodal regime. So there is one well-defined peak in rainfall in the summertime, okay? I mean, broadly speaking, people sometimes, include in the North American monsoon also the typical rainfall you have, for example, over further south over Central America, okay? Like Belize or Costa Rica. So here also we have a rainy season, which is during the summer, but the regime is bimodal because you tend to have two peaks in precipitation in June and September with a local minimum in July and August. So this is also called the midsummer droughts, okay? And I mean, overall, I mean, they can be considered part of the North American monsoon system, even though a stricter definition just include this region here, okay? Then if you, for example, look in the southwestern US, it's again bimodal because you have a peak in summer associated with the North American monsoon, and then another peak in winter associated with the westerly storms. All right, so of course, as for South America, the North American monsoon is very important for the population because as all the monsoons, it provides a very large share of the annual precipitation, especially for Mexico, I would say, for Western Mexico. So it's very important for agriculture, and also it's strongly associated with extreme precipitation events, like flash floods. So the type of rains we have during the North American monsoon is of a convective nature, so either convective or mesoscale convective systems. So often they give rise to very intense precipitation event. If you take the chapter 8 of the latest report, the latest assessment report of the IBCC, the authors tried to summarize the current change of regional monsoons. When you look at the North American monsoon, what you see, both in observations and in models, is that there is not really a strong trend, okay, in the mean precipitation. So observations have weak positive trends, and you can also see that here. There is not, there is variability in observations, but not really a strong trend. And simulations of couple models tend also to show a weak trend, which seem to arise from a compensation between the aerosol effect and greenhouse gas effect. But it's not as strong as, for example, it's in the case of the South Asian monsoon, okay, where the two contrasting effects are really large. So a better, more visible trend is instead, we can appreciate that in the extreme precipitation, okay? So for example, here we see a comparison between 3 different data sets for the southwestern US, which is also interested by the North American monsoon. And you see that there is an increase in the extreme precipitation, okay? This is, I think, is the 99th percentile. You see there is more red than blue. And this has been confirmed in a number of studies. This is from Luong et al., but also in a more recent one by De Maria. However, we have to say that these results are mostly for the northern margin of the North American monsoon, for the US, for Arizona, New Mexico, where there is a very dense network of gauges, but there are not many observations, or at least long-term observations for Central America or Mexico, for example, which is really the core region of the North American monsoon. So observations suggest small trends. We also have to say that these trends, are in general also associated with the decadal variability, which is very important, as it is for the South American monsoon, also for the North American monsoon, which is an area surrounded by the Pacific and Atlantic, so it's influenced a lot by what happens in these two oceans. There is overall limited knowledge of what's going on in terms of trends in Central America and Mexico. And there is, let's say, we have more confidence instead in an indication about the increases of extremes, especially in the southwestern US, okay? So when instead people try to look at future projections, the indication from models is of an overall reduction of summertime rainfall over the North American monsoon, which is again contrasting with what is observed for the other monsoons. So overall, global monsoon land precipitation is projected to increase in both CIMI 5 and CIMI 6 model, which you can see here, okay? So this is for all the monsoons, and it's consistent with the strengthening of the hydrological cycle. But when you look at the North American monsoon, the red arrow, you see that the projection is very different from the other monsoons, especially the Asian monsoons, okay? Let's see that a little bit more in detail, and let's look at the spatial patterns. So this is an updated projection from CIMI 6, sorry, so from 2022. And looking at that, we can see that the overall small reduction, which is also projected by models, mostly arises in the southern part of the region, so basically Central America, okay? And it's most prominent in June, July, August, and whereas there is a reversal of the sign in the late summer, early fall. Also, if you look at the core region of the monsoon, you see that again trends are not strong, and there is a large, so for example, if you look at the state of Chihuahua or Sonora or Sinaloa, which are the really core monsoon regions, there are not strong trends overall, okay? So it would seem that there is not like a strong confidence in these results. So if you read the IPCC 5, what you can read there is that there is low confidence in projections of changes in precipitation amounts for the North American monsoon. And the updated version of this statement is both where authors also considered lines of evidence from paleoclimates, is that both paleoclimate evidence and observations indicate an intensification of the North American monsoon in a warmer climate. But again, the statement comes with the medium confidence. So overall, we have low to medium confidence in these projections, okay? Which overall, it seems to be a problem of also other monsoons, as shown before. So, but where are the issues? Why such a low confidence? Where does it come from? Why it's so difficult to get a reliable simulation of the North American monsoon? So, as I said at the very beginning, this is a monsoon which extends over a very small area, okay? Now, in this plot, you can see a typical resolution of a general circulation model, which was probably state-of-the-art 20 years ago, okay? So 200 kilometers of resolution. And you see that here, given this resolution, the model doesn't capture, for example, well, the topography, but it doesn't even capture the Gulf of California. So it doesn't capture all the finer scale geographical features. No. So now current models have a higher resolution. So they probably are around 100 kilometers, okay, on average. Which is better, but still, I mean, you don't capture well the Gulf of California. So this is an issue because a very nice recent paper by Johnson and Delworth shows what are the effects that you have in the simulation of the North American monsoon if you don't properly represent the Gulf of California. So most of models of GCMs with coarse resolutions, or even with a resolution of 100 or 50 kilometers, have a Gulf of California which is either covered by land because it's not represented, or is partially covered by land, okay? So in this study, they took a 50-kilometer resolution model, and they explicitly include, they had two different rounds, one in which they covered the Gulf of California with land, and one in which instead they properly represented as a sea, okay? And so you see the impact, for example, on the low-level winds, which is very dramatic. So if you don't have the Gulf of California, so if you don't have sea there, the model doesn't capture the southerly flow, which is typical of the monsoon season over the Gulf of California, which is very important for transporting moisture into the southwestern US and northwestern Mexico. So it's a very large impact on the flow, especially the low-level flow, which turns into a large bias in terms of precipitation, which is basically an underestimation of rainfall over a large part of the southwestern US and northwestern Mexico, okay? So that's a bias which comes from the fact that the model has a two-course resolution to capture, to resolve these geographical details in a region which is very small and narrow in a way, okay? Second source of problems comes from sea surface temperature biases. So as you know, couple models develop errors in the simulation of sea surface temperatures, and these biases are transmitted to the circulation of the atmosphere and seem to cause what is called the retreat problem from the North American monsoon. So what you see here is a comparison between the models and observations for the monsoon signal. And the retreat problem means that these models overestimate precipitation in the late part of the season, like in the retreat phase of the monsoon. And a number of studies, amongst which I want to point out to the one by Ian Wang, which is very recent, managed to identify what are the biases which cause this retreat, and are biases especially over the Pacific Ocean. Also, the presence of sea surface temperature biases makes the response of the North American monsoon very uncertain, because the North American monsoon is very sensitive to sea surface temperature biases. For example, in this study, we took a high-resolution model, 50 kilometers, and we had 2 runs, 2 experiments in which we doubled the CO2 concentration. So in the first one, we ran the coupled model as it was, and in the second one, we removed sea surface temperature biases through flux adjustment. So you can think of a simulation with a model which develops biases and another one which does not develop biases. And in the 2 cases, we saw a strong difference in the response of the North American monsoon. So in the biased version, there was not an overall reduction. In the other one, there was a strong reduction of the precipitation, especially in the northern part of the monsoon and the northwestern Mexico. Now, the model can also be not right, this model, and this response can also be not the one which we'll observe, but the study is more about pointing out that until there are sea surface temperature biases in the nearby oceans, these have a strong impact on the response of this monsoon. And so this, of course, erodes our confidence in these results. Also, if you combine sea surface temperature biases and, let's say, coarse resolution biases, those effects can combine in an uncontrolled way. This was shown by Meyer and Jean in 2017, where they took first a global coupled model and they did the projection for the future. They observed some reduction of precipitation. Then they downscaled the model, so they had the proper representation of orography and the Gulf of California. And you see that already the response starts changing. You don't see anymore any decrease of precipitation in the southwestern US. Then they also removed the sea surface temperature bias from the model. And I mean, you see that you have a totally different response, which is an increase in precipitation. So this means that those 2 biases, which are of different nature, combines generally models and can produce very large intermodal variability, okay, intermodal differences. Finally, another very recent study by Wallace and Minder points out to another issue which may undermine the capability of models, of GCMs, which is the way they represent convection. So in the North American monsoon region, as I said, the precipitation is during summer is mostly of a convective nature and often convection organized in mesoscale convective systems. And so they analyzed a pseudo-global warming run, 12 years long. And they noticed that in this run, when convection is not parameterized, but is partially resolved with convection permitting models, there is an increase in precipitation. Now, here some caution is needed because this is just a 12-years long run. And as we said, probably it's not long enough to detect a trend, a forced trend. But I mean, it points out to another potential issue, okay? And finally, there are still, I think, some more fundamental problems with the North American monsoon is whether we really understand well what are the causes and the mechanism that produce it. Traditionally, the North American monsoon has always been viewed like a sort of giant breeze circulation, which is thermally driven by elevated heating over the Sierra Madre mountains of Mexico, so by the Mexican topography. In a study in 2021 by Bill Booz and myself, we did some idealized simulations with high-resolution GCMs, 25 kilometers of horizontal resolution, in which we flattened, we either keep the orography as it is in reality, or we flattened the Mexican topography. And then what you can see from, if you compare control and flat max, is that if you flatten the topography, the very characteristic band of rainfall, which is along western Mexico, disappears. Looking a bit more into the dynamics of the response, what we find out is that the topography over Mexico originates a stationary Rossby wave, which is associated with these two gyres here, which is associated with an enhancement, strong enhancement of the westerly flow in the lower atmosphere. And this westerly anomalous flow originated by the stationary Rossby waves is crucial for bringing very moist air, which originates over the Gulf of California upslope over hills and to generate convection. So this seems to point out to the fact that at least an important part of the North American monsoon is that it's not a totally thermally driven system, but is mechanically driven by the orography. So the paper, the study, there was also, the hypothesis that was not completely thermally driven was tested by taking the setup with no Mexican topography and lowering the albedo, so that the insolation, the absorbed solar radiation at the land level could be increased. And we see that this was not enough to generate, again, the typical band of rainfall over Western Mexico. So to sum up, and to give some directions and perspective for the future research, we can say that up to now, the impacts of anthropogenic global warming on the North American monsoon are still quite modest. So trends and in the mean summer precipitation are either small or insignificant, whereas there is some indication of an increase in extreme rains. So in terms of projections, they are of low to medium confidence, which is not what stakeholders and users would like to hear. I showed that the origins of these problems is in a number of issues, not one issue, but a number of different issues of different natures, which combine together. And so they are due to large-scale sea surface temperature biases in adjacent oceans, unresolved mechanisms due to unresolved geography and orography, inadequacy of GCMs in representing convection, because it's in most of GCMs, it's parameterized, actually, well, in all, I would say. And still, an incomplete understanding of the basic mechanisms, which are also important to build our confidence in what a GCM can simulate, okay, to understand what a simulation is. So for the future, we may think that since GCMs have a resolution which is increasing, is increasing in the course of time. Typical resolutions nowadays are higher than used to be 10 years ago and 20 years ago. So we may imagine that going for models and GCMs at even higher resolution may alleviate and heal some of these issues. Also, we are in a moment in which convection permitting models are being devised and run not just for limited regions, but also for global domains, even though still with very limited time duration. But we may think that in the coming years, general circulation models may start being will start being routinely run with convection, with resolved convection. So this again may alleviate some of these issues. Also, I think what we also need is to continue to better understand the basic mechanisms of the monsoon, as shown by the last paper. So, for example, for other monsoons, like the Asian monsoon, there have been a lot of studies of this sort of idealized studies, okay? This was prevented for the North American monsoon, mostly because until 20 years ago, models were not of high resolution enough. But now we have GCMs of resolution of 50 kilometers, 25 kilometers. And so more idealized studies, I think, will help to better understand, for example, the role of mechanical versus thermal forcing. And so with this, I would end, and I thank you all for your attention.
Thank you very much for your excellent talk, Salvatore.
Welcome.
As I understood from the two talks, the main issues here are the predictability in the predictions, how to improve the predictions during the monsoons. You mentioned several problems that might let's say, worsen the predictions related with orography, for instance, with SST. And a problem that I also think is every day more serious is the problem of providing to the users robust and actionable climate change information. Because you showed how in North America monsoon, this information is not very reliable. And when you look at the total annual rainfall, the changes are small and sometimes not congruent among different models. Pedro, Leite, Silva Diaz also showed this aspect of differences between different models. I think this is a problem that we need to look seriously at, to provide robust information, because the information we have nowadays doesn't seem very reliable. You very frequently cannot take actions or cannot plan for the future based on this kind of information.
Alice may have frozen there. Yeah. Paulo, do you want to take over a minute while she reconnects?
Yeah, I think
you're back.
Yes, I think I lost my connection. Are you?
Welcome back.
Can you hear me?
Yeah, you're fine now.
Okay. Okay. So, well, this kind of information, total changes in total annual rainfall or total monsoon season rainfall, is not actually very actionable. I think people would like to have information about what happens at the beginning of the monsoon, at the peak monsoon season, at the demise of the monsoon. When we look with greater temporal resolution, we see that these responses are different. So they change from, I would even say, from month to month. So looking at these totals doesn't give very useful information. And just to, before the questions and answers, and perhaps this would also help people to ask questions, I would like to share let me see here. Okay, share the screen. Let me share something that I prepared. Share? Okay. So, Okay, so about these challenges, as I said, the two main challenges that I see are about prediction, in predictability, and robust and actionable information on climate change. Just to give a hint about the problem we have here in South America about prediction and predictability at the peak of the monsoon season. You can see here in this figure, the first mode of variability during December, January, February, which is the peak of the monsoon season. It's a dipole-like pattern with opposite signs between Central East South America and Southeast South America. And it happens at intraseasonal, interannual, and interdecadal time scales. And well, this dipole is very much influenced by regional circulation that happens here. When we have here a cyclonic circulation, regional cyclonic circulation, then there will be more rainfall here in the northern part of the dipole. And when it is anticyclonic, we will have more rainfall in the southern part of the dipole. And this can be, this kind of regional circulation can be influenced not only by teleconnections, by wave trains coming here from South Pacific, but also can be influenced by surface atmosphere interactions at a regional scale. A study we carried out some years ago showed that there is an inverse relationship between this mode in spring and in summer. It tends to reverse the polarity of the dipole from spring to summer because of surface atmosphere interactions that are triggered by soil moisture. That means precipitation anomalies in the spring. And here you can see it very clearly. In black, you have the climatological precipitation. And when you have more rainfall here in spring, you tend to have less rainfall in the peak summer. Here, another view of it. For in this region here. So we tested an hypothesis and with a regional model, and it was confirmed by the results of the model, the reason of this tendency to reversal. Well, this means that when you in spring have less than normal rainfall in this region here in Central East Brazil, you tend to have above normal in peak summer. But most of the models do not reproduce this kind of behavior. And you can see it here. When you look here at an evaluation and assessment of skill, here, this is from the site of ECMWF. For spring, you have a rather good skill here in this region in spring. But look what happens in summer, in peak summer. It drops very significantly because the models even tend to persist what happens in spring and to the summer. And there are also other examples I look at for in articles. You can see that from the first week of subseasonal forecast to the third week, this region here, the skill in these regions has the strongest drop in all South America, from the first to the third season. But this, when you look at an extended season, from November till March, But when you look just for December, January, and February, you don't have this very strong drop in the skill. And what's the reason? Because when you evaluate the skill from November till February, you can have the beginning of your prediction in the spring and the date of the prediction in summer. So the error is much higher. But when you look just, this is a study we did some years ago. When you look just at December, January, February, in the third week, you still have a very good skill. Well, so I think this is a problem that we have to face, because it's the most important period to have good predictions. Do you have some comments on it before the questions, or do we go now to the questions first, and then we leave these comments to the end, for the end? You are muted, Pedro and Salvatore.
Yeah, we can go to the questions, I think. There are several questions.
Okay.
I already answered some, but there are still some that have not been answered. Who's begin? Can I go on and answer some of the questions?
Yes, of course.
Okay.
Go to the Q&A box and
yes,
then
the Q&A box. Yeah.
yes.
Yeah. One of the questions is related to this issue about the interaction of the South Atlantic Convergence Zone with the ocean. This is an important point, because in general, when we have a very active South Atlantic Convergence Zone, the sea surface temperature below the South Atlantic Convergence Zone is cold. So it's not really warm. This implies that there is a very strong interaction between the ocean and the atmosphere and the location of the South Atlantic Convergence Zone. Something that from my experience looking at models, indicates that the atmospheric models are not really doing a good job. One of the reasons, I think, and it's partially related to the point that Alice brought up concerning the continental portion of the convection and during the monsoon season, the effect of the interaction with the surface, is something that called my attention observing radar data along the South Atlantic Convergence Zone, at least over the continent and near coastal areas, indicating that there is a substantial amount of precipitation from warm clouds. Models don't like warm clouds because the convective parameterizations tend to induce big convective towers if you have a convective instability at the lower levels. They rely a lot on the surface convergence, and therefore they overestimate the height of the maximum heating, diabatic heating associated to convection. And this in turn has a very important impact on the organization of the circulation anomaly associated to the heat source induced by the South Atlantic Convergence Zone. So that's, I think, is one of the reasons why when we look at very high resolution simulations of the South American monsoon with few kilometers, cloud resolving models, we have a different picture. And I bet it's the same thing in the North American monsoon system. In some places, perhaps this is exactly the same problem. In other words, the partition between deep clouds and shallow clouds convective heating is not really good in the models. And so that's the point that I'd like to point out, answering some of the questions that were brought, including some concerning the, for instance, what are the challenges for modeling this area? First of all, I don't think that atmosphere-only models can help us very much, because if you have a warm SST, they're going to put a lot of precipitation over the spot. But if you have a ocean atmosphere model, you may get a different response. And that's exactly what we see in the papers that were published in the last 10, 15 years or so with coupled oceanic atmosphere models. I think that covers pretty much the questions that were sent to me, and some I already sent a detailed answer. Okay.
Okay.
Salvatore?
Uh-huh.
Yeah. I have probably a couple of questions. So there was one by Laila Carvalho, who was asking about the role of low-level clouds. So given the importance of these clouds for Central America, could you please provide your perspective on the implications of this for future projections of the North American monsoon system? So probably, as far as I know about connections between low-level cloudiness along coastal California and the North American monsoon, in a sense that the moisture flux associated with the North American monsoon can influence cloudiness. I mean, there was a very recent paper I read by Clemente et al., but I'm not really aware about whether low-level clouds themselves can influence the North American monsoon. So I don't know what this mechanism is for Central America. So if you can comment on that, because I'm not really aware. So I don't really know how low-level clouds can influence the North American monsoon, but I'm wondering what the mechanism may be for Central America or South America. Not really sure about that. And there was also another question about is there a relation between the forcing of the stationary orographic wave and the NAM onset? What changes in the level of atmospheric circulation lead to forming of the stationary orographic wave? So in that paper, in that study, we did observe a change not only in the total amount of rainfall, but also in the timing of the monsoon. But we didn't really focus on that. We didn't really analyze that in detail. So that is an interesting point to further investigate, I would say. And about the mechanism leading to the formation of stationary wave, I would say that those are the typical mechanisms you observe when an orography forces a stationary Rossby wave. In terms of flow at the low level, the orography of Central America and Mexico is crucial for diverting the easterly flow from the Atlantic northwards into the low-level plains. So in creating the Great Plain low-level jets, okay? So you may think that if the Mexican orography was not there, the easterly flow will not deflect northwards, but continue straight into the core region of the monsoon. And so that would not permit a westerly level flow from the Gulf of California over the hills of the Sierra Madre. But yeah, overall, I mean, it's just the classical Rossby wave, stationary Rossby wave generated by and mounted by orography. And so if you look at the global scale, that feature is really global, and it goes along arches, like stationary Rossby waves do.
Lisa, can I answer another question that I hadn't noticed? It's by Ian Verden. Actually, it has to do with the impact of sea surface temperature on the monsoon. It was partially covered in my previous answer, but there is something that I'd like to say about this. In fact, the dipole that Alice mentioned, the Southeast South America dipole, appears in different scales, as she showed in the slides, but it also appears in paleoclimate studies. So it's there in all scales. And when you look at from the paleoclimate point of view, something that strikes me is this issue about the positioning of the ITCZ. When you look at the paleoclimate time scale, the ITCZ position change is very large. If you consider the transition not only from last glacial to the current period, but also bursts of deglaciation since 20,000 years ago to the near past. For instance, at around 8,000 years ago, there was a burst of ice melting that induced significant changes in the AMOC, in the Atlantic Meridional Overturning Circulation. And as a result, the ITCZ moves around. There has been some periods, for instance, that Northeast Brazil was pretty wet. The ITCZ was actually located to the south of the equator, something that we don't see today. We see some drifts momentarily for a few months, but then it goes back and the mean position is well to the north of the equator. But at that time, it was pretty much located south of the equator. And that, I think, is a very relevant concern in terms of modeling needs to increase predictability of what's going to happen with global warming. The coupling between, not just the coupling with the surface processes, but the coupling with the ocean from the point of view of the model representation of the heat transport, the meridional heat transport in the ocean. And that's what drives the position of the ITCZ. As a result, when you look at past climate in a situation where the ITCZ was further to the south, the South Atlantic convergence zone was quite different. Not just to the south, right? But the location, whether it was stronger over the continent or stronger over the ocean. So that, I think, is the reason why we should keep a lot of attention to the PMIP results, not just CMIP, but PMIP, the past climate. And something that I was pretty happy to see what they're planning for the next version of CMIP 7, and PMIP, I think, is number 5. Many more studies, including transient simulations, not just a stationary forcing, which is representative of a certain period, 6,000 years ago, 10,000, 8,000 years ago, 20,000 or so. No, it's a continuous simulation of what happened in the last 20,000 years, including the forcing due to the ice melting. And I think that will give us a much better confidence on which models are better from a point of view of the positioning of the ITCZ, which is crucial for the monsoon here in South America, in Africa, and I think it will also have some impact in the North American monsoon because of the impacts in the position of the ITCZ in the Pacific, in the Eastern Pacific.
Okay, thank you, Pedro. Rajagopal, do we have more questions to answer, or are we done?
All are answered, I think. All are answered.
Pardon?
All are answered.
All are answered. Okay. Yeah, I just saw one here, but I don't know, perhaps Pedro has already answered it completely, but I would like just to complement. It's from Ian Verdon. I would like to ask a question, bearing in mind that we are observing significant changes in SST. How can these changes affect the monsoons, and what are the obstacles to making climate forecasts for these regions? Well, this actually fits.
That's the one that I answered, Lisi. That's the one that I touched the question. I answered partly just a few minutes ago.
Yeah, I know, but I wanted just to complement because I noticed that perhaps he was talking about also a future climate. How can these changes affect the monsoon, and what are the obstacles to making climate forecasts for this region? I'm not sure if he is referring just to climate forecast in the present time, or climate projections. But anyway, this is fits in the context of robust and actionable climate change information if his intention was to know about climate projections for the future. Actually, as I said before, these changes are usually shown in terms of total annual rainfall or total seasonal rainfall for the monsoon season, for instance. And then in South America, these changes for the future are usually very small. And for multimodal ensemble, you can see it in the IPCC internet site. You can even look at these figures and choose the periods you want. There is a great disagreement, besides being very weak, these changes, there is a very big disagreement between models about these changes. So they are really not reliable. Then I decided to look in short periods, bi-monthly. And I was really very surprised because I recognized some of these patterns of these future changes. They look at very much alike the El Nino impact patterns during the peak monsoon season, including the tendency to reverse the sign from November, from the beginning of the monsoon season to the peak of the monsoon season. Well, there is a reason for this. When you look at the change, the future change of SST, you see an enhancement, an increase of SST in equatorial Eastern Pacific, just the El Nino pattern, which indicates that you will have stronger El Niños in the future, because the highest enhancement of SST is just in the region where the El Nino has the strongest components of variability, the ENSO, the El Nino, La Nina oscillations. Looking at the models, we concluded that not always and generally the best criterion for choosing models is not just looking at how they reproduce, how they simulate the present-day climatology, but to look at how they simulate El Niño and La Niña and the oscillation. And this is a pretty hard task, because you have to look at each of these runs of the models. And so we look at the 3 runs of each model to see if there was a consistent behavior for each model among the different runs. And then look at the results of these models that best simulated El Niño and other models. And then you can get a much stronger signal of future change. So then you have a dynamical framework to explain these changes. And this would give a more robust information also for the users. So that's my comment on this. So,
There is a question
else?
for you, Alice, by Reinaldo Haas.
Reinaldo? Okay. However, there is well, yeah, actually, I wouldn't have a very precise answer for this. I have already talked to Reinaldo about this issue. And I wouldn't say, I wouldn't know what to say about this soil management. What would be the difference? What would be the impact in this influence of spring soil moisture on what happens in peak summer? So I really don't have a very precise answer for this right now. Perhaps.
Can I make a comment about this? I'd like to make a comment about this.
Okay.
This question actually reminded me of an old paper by Charney back in the early 70s on the desertification of the Sahara, the southern Sahelian, the southern part of the Sahara, and the land use. And it makes sense in the sense that the changing the surface cover has a very significant impact on the energy balance of the Earth system locally. And that in order to provide the necessary conditions for sustainability of water in the soil, you need vegetation. If you don't have vegetation, not going to keep water in the soil. So, and that I think, as he mentioned, it's true. There are experiments, not large scale, but mesoscale or even more, smaller than that, indicating that there is a significant impact. And not only for this reason, but also in terms of for water security. Having water for urban areas and livestock. So I think I've seen some papers recently that reminded me of this paper by Charney, but most of them don't quote Charney's old paper back in the early 70s. I think they should read it.
I just wanted to comment to Reinaldo is that what these models that represent, that simulate well and so on, show is not actually a drying in this region in Central East Brazil. No. So I don't see in this future projection of these more reliable models indications of desertification in this region which is crucial for this effect of reversal of sign from spring to summer. They don't indicate drying in this region, contrary to other models that do not represent well answer.
Yeah.
So I don't see this indication in more reliable models.
Yes, I think
just-
this is a very important point that Alice made. When you look at the CMIP models, you have everything. So how do you choose what's the most probable response? I always remember a talk by Shukla. I think it was in IPCC number, I don't know, it was in 2004, 2005, something like that. He showed very interesting figures showing that, indicating that models that have a rather extreme response usually did not produce a reliable representation of the 20th century climate. So in other words, you actually have to have to provide different weights for the models in terms of how well they produce. The problem is, what's the metric for evaluating how climate is good? ENSO is one of the metrics, of course, but there are others. In our case, for instance, we were very much influenced by the Atlantic Ocean. And that's tough because most of the models do have a hard time in reproducing properly the South Atlantic, the Brazil current, for instance, the splitting of the equatorial current and the Brazil current to the north, Brazil current entering into the Caribbean. So we have to be careful with that thing, those details. And that's the models that do a better job in representing the oceanic circulation, I think, are those that we have to pay more attention.
Okay, well, I think time is over. And well, I would like to thank very much to the speakers for the excellent presentations. Would like also to thank to the participants for their questions, which always give way to very interesting discussion. And I want to thank also for the support, technical support, that made possible this webinar. Thank you very much, and till another occasion.
Thank you for inviting us.
It's my pleasure. Thank you for accepting.